Welcome back, everyone, for another deep dive today. Today we're going to be looking at something really cool. The intersection of math and art, and specifically the work of Henry Segerman.
So for the next, 30 seconds or so, we're going to be talking about how Segerman's art really brings these complex mathematical ideas to life. And we're going to focus especially on stereographic projection.
Stereographic projection, yeah.
And its reach into other fields like crystallography.
Yeah, that's a really good example.
And by the way, while we're on the topic of supporting us, could you help us hit 1,000 subscribers on YouTube today?
Yeah, that would be awesome.
That would be amazing.
Yeah.
All right, so back to Segerman. He's really remarkable in how he makes abstract mathematical concepts tangible.
Yeah, he really has a knack for that.
Yep.
Consider this one installation he did with a transparent sphere on a lighthouse, and it's lit from its north pole.
Oh, yeah, I've seen that one.
Have you seen that one?
Yeah, it's amazing.
Isn't that cool?
Yeah.
It's a seemingly simple setup, right?
Yeah, totally.
But it beautifully demonstrates this whole principle of stereographic projection.
Yeah, it's a brilliant illustration.
Right.
Like, it really makes you kind of see the idea immediately.
Exactly.
So, yeah.
So how does it actually work, though?
Well, so you know how in stereographic projection, you imagine a light ray coming from the very top of the sphere.
Right, the North Pole.
Exactly, the North Pole. And then it travels straight through the sphere. And then it keeps going outwards, right, in a straight line.
Yeah.
And then wherever that ray hits a flat surface,
right,
which in the lighthouse would be the ceiling, that point is basically the projection of that point on the sphere.
So it's like taking a 3D object and kind of flattening it onto a 2D surface.
Exactly. And it,
in a very specific way,
creates these really interesting visual changes.
Right.
And it reveals these underlying mathematical relationships.
Yeah. For example, I understand that shapes at the center of this projected image, they stay about the same size as they were on the sphere originally.
Exactly. And that's what's so cool about it, right? Because as you move away from that center point, things start to get bigger.
Yeah.
And more stretched out.
Oh, that's interesting.
Yeah, compared to how they were on the sphere.
So it's not a uniform distortion across the whole image.
Exactly. It's not like you just took the sphere and squished it flat. It's much more nuanced than that.
Yeah.
And it has to do with how the light rays are kind of diverging as they leave the sphere.
Right. So the further away they get from the point directly below the North Pole, the more spread out they are.
Yeah.
So it makes sense that things would get magnified.
Exactly. It's like if you imagine shining a flashlight on a wall, the further you move the flashlight away, the bigger the circle of light gets.
Oh, I see. I see.
So it's a similar principle here.
Yeah. So it's like how on a map, you know, the continents near the equator look pretty true to size, but then things get really stretched out as you get closer to the poles.
Yeah, exactly. That's
the analogy. But what's really cool is that some things don't get distorted in this process, right?
Oh, yeah, absolutely.
Like certain aspects stay the same.
One of the most important things that stereographic projection preserves is angles.
Oh, interesting.
So if two lines or curves on the sphere, they intersect at a certain angle.
Right.
In the projected image, they'll intersect at that exact same angle.
Oh, that's cool.
Yeah, it's really neat.
So that must be really important for certain applications.
Oh, yeah, totally. Like, think about map making. You want to make sure that the angles between different landmarks are accurate.
Right, or like navigation.
Exactly. Yeah, you don't want to be sailing in the wrong direction.
So it's not just about preserving shapes.
No. Not at all. It's also about preserving these relationships between them.
Right, these angles.
Yeah.
And there's something about circles too, right?
Oh, yeah. That's another really cool thing about stereographic projection. Any circle that you have on the surface of the sphere, as long as it doesn't go through the North Pole itself, will always be projected as either another circle.
Oh, wow.
Or if it does go through the North Pole, it'll be a straight line on the plane.
That's so cool.
Yeah, it's pretty amazing.
So these circles, they kind of stay intact in a way.
Yeah, they maintain their circularity in this projected space.
I love that word, circularity.
I know, it's a good one.
That's amazing.
So yeah, it's not just any random distortion. It's very specific, and it has these really interesting properties.
Yeah, and this isn't just a standalone art piece, right?
No, this is actually part of a bigger project called Mathmalchemy.
Oh, right, Mathmalchemy.
Yeah, have you heard of it?
I have, yeah.
Yeah, it's amazing. It's basically this huge collaboration between all these different mathematicians and artists.
How many?
I think there were like 24 involved.
Wow.
Yeah, it's a big project.
And so Segerman was one of them?
Yeah, he's a key player in it.
And what was the goal of Mathmalchemy?
Basically to create this multimedia installation that celebrates the beauty and creativity of mathematics.
So it's like taking these abstract ideas and making them accessible.
Exactly, and showing that math isn't just this dry, boring subject. Yeah. It can be beautiful and inspiring.
Yeah, and Segerman's lighthouse piece is like one part of this bigger picture.
Yeah, it's a perfect example of how you can take a complex mathematical concept and turn it into something that's both visually stunning and intellectually stimulating.
And it sounds like stereographic projection itself is more than just this mathematical curiosity.
Oh, yeah, for sure.
Given that it has all these applications in other fields.
It's a fundamental tool in mathematics, and it pops up in all sorts of unexpected places.
What's so remarkable about it?
Well, you're basically taking this curved surface, right?
Yeah, a sphere.
A sphere, yeah.
And flattening it out.
And flattening it out onto a plane. But you're doing it in a way that preserves a lot of the important information.
Right, like the angles.
Yeah, the angles especially. And that's really important for a lot of applications. Like I mentioned map making and navigation before. But it also comes up in things like theoretical physics.
Oh, wow.
When you're analyzing fields and stuff like that.
So it's not just about making pretty pictures.
No, not at all. It's a really powerful tool for understanding how things work.
And it's this idea of a conformal transformation, right?
Yes, exactly. That's the key property.
So that means it preserves those local angles.
Exactly.
Which is vital for accurate maps.
Yeah.
And even for theoretical physics.
Yeah, it's all about maintaining those relationships between things.
And the way it transforms circles, too. That must be important.
Oh, yeah, absolutely.
You know, keeping them as circles or turning them into lines.
Yeah, that has a lot of uses in complex analysis, which deals with complex numbers.
Yeah, I remember those from college, vaguely.
Yeah, they can be tricky, but stereographic projection makes them a little bit easier to work with.
And in crystallography, too, right?
Yeah, that's a big one.
Crystallography, that's the study of crystal structures.
Yeah, basically how atoms are arranged in solids.
And the stereographic projection helps with that.
It's essential for visualizing those structures.
So it's like a bridge between geometry and the real world.
Exactly. It connects the abstract to the concrete.
And then there's this idea of the Riemann sphere.
Oh, yeah, that's a cool one.
I've heard of it, but I don't really understand it.
So basically, you take the complex plane, which is like a 2D plane where each point represents a complex number.
Okay.
And you add a single point at infinity.
A point at infinity. What does that even mean?
It's kind of hard to visualize.
Yeah.
But mathematically, it makes sense.
Okay.
And when you do that, the whole thing becomes topologically equivalent to a sphere.
So you're like wrapping the plane around a sphere.
In a way, yeah, it's a bit mind-bending, but it's a really powerful concept.
And that's called the Riemann sphere.
Exactly.
And it helps mathematicians study functions.
Yeah, it's a key tool in complex analysis.
So this is getting pretty advanced.
Yeah, we're diving deep here.
But even beyond these theoretical realms, stereographic projection has these practical applications, like in map making.
Oh, yeah, absolutely.
You mentioned that earlier.
Yeah, so there are these things called azimuthal projections, which are basically maps that are based on stereographic projection.
Okay.
And they're really good for mapping the polar regions of the Earth.
Why is that?
Well, because they maintain angles really well.
Right, we talked about that.
Yeah, and that's super important for navigation near the poles.
Yeah, you don't want your compass to be off by a few degrees when you're up there.
Exactly.
And there's a specific projection for the polar regions, right?
Yeah, it's called the Universal Polar Stereographic System, or UPS for short.
UPS, like the delivery company?
Yeah, exactly. It's kind of funny.
That's great.
But yeah, it's the standard projection used for maps, the Arctic and Antarctic.
Cool. And what about in fields like topology and differential geometry?
Oh, yeah. Stereographic projection comes up there, too.
How so?
Well, you can actually extend the basic idea of stereographic projection to spaces with more than 3 dimensions.
Whoa. More than 3 dimensions?
Yeah, it gets pretty abstract.
Yeah, I can imagine.
But it's really useful for studying these things called manifolds.
Manifolds?
Yeah, they're basically curved spaces.
Okay.
But they can have any number of dimensions.
So it's like a generalization of a surface?
Yeah, you could think of it like that.
And stereographic projection helps mathematicians visualize and understand these manifolds.
Yeah, it gives them the way to kind of flatten them out.
Okay.
And study their properties.
And you also mentioned it has a historical connection to astronomy.
Oh, yeah, that's right.
What was that about?
So back in medieval times, Arabic astronomers used these instruments called astrolabes. Yeah, they were pretty sophisticated for their time.
What did they do?
They were used to measure the positions of stars and planets.
Oh, wow.
And the design of astrolabes relied directly on the principles of stereographic projection.
How so?
Well, they basically used it to represent the celestial sphere on a flat surface.
So they were like ancient map makers of the sky.
Yeah, in a way.
That's amazing.
It's a really clever application of geometry.
So we've seen how stereographic projection connects art, mathematics, map-making, astronomy.
Yeah, it's all over the place.
It's like this unifying thread.
Totally.
And you mentioned some advantages in fields like physics, chemistry, and engineering.
Oh, yeah, right.
Can you give some specific examples?
Sure. So in physics, you can use stereographic projection to visualize force fields.
Like magnetic field?
Yeah, exactly. So you imagine these lines of force.
Yeah.
And the angles between them are really important for understanding how the field behaves.
Right.
And stereographic projection lets you represent those angles accurately on a 2D surface.
So it's like a way to see the invisible.
Yeah, in a sense.
Cool. And what about chemistry?
So in chemistry, you often use X-rays to study the structure of crystals. And when you shine X-rays at a crystal, they diffract.
Diffract.
Yeah, they scatter off in different directions. And the pattern of diffraction tells you a lot about how the atoms are arranged in the crystal.
Right.
And stereographic projection helps you analyze those diffraction patterns.
How so?
Well, it lets you visualize something called the reciprocal lattice.
The reciprocal lattice?
Yeah, it's basically a mathematical representation of the crystal structure in a different space.
Okay.
And by looking at the reciprocal lattice, you can figure out things like the distances between atoms and the angles between bonds.
So it's like a key to unlocking the secrets of the crystal.
Yeah, it's essential for understanding how crystals work.
And what about engineering?
So engineers often need to create 2D models of 3D objects.
Yeah, for blueprints and stuff.
Exactly. And stereographic projection can be really useful for that.
Well, because it preserves angles.
Right.
So you can make sure that the angles in your 2D model are the same as the angles in the real 3D object.
Which is important for making sure things fit together properly.
Yeah, exactly. You don't want to build a bridge that collapses because the angles are wrong.
Right.
So stereographic projection helps engineers create accurate and reliable models.
So it's like a bridge between the theoretical and the practical.
Yeah, it connects the world of math to the world of engineering.
Okay, let's focus a bit more on crystallography, since that seems like a particularly significant application.
Okay, yeah, crystallography is a great example.
How does stereographic projection help us understand crystals?
Well, one of the key things it does is it lets us visualize the symmetry of crystals.
The symmetry.
Yeah, so crystals have all these different symmetries, like they can be rotated or reflected, and they still look the same.
Right, like snowflakes.
Exactly. Snowflakes are a perfect example.
They have six-fold symmetry.
Yeah, you can rotate them by 60 degrees.
And they look the same.
And stereographic projection helps us see those symmetries.
Yeah, it lets us represent them in a 2D format.
Okay.
So imagine you have a crystal,
Uh-huh.
and you surround it with an imaginary sphere.
Okay.
And then you project all the symmetry elements of the crystal onto that sphere.
So it's like making a map of the crystal symmetry?
Yeah, exactly.
Right.
And then you use stereographic projection to flatten that sphere onto a plane.
So you end up with a 2D representation of the crystal's 3D symmetry.
Exactly. And that's really useful for understanding how the crystal is put together.
So, for example, you mentioned rotational axes.
Yeah, so if a crystal has a threefold rotational axis.
Right, so you can rotate it by 120 degrees and it looks the same.
Exactly. Then in the stereographic projection, you'll see 3 points arranged in a circle.
Representing that axis of symmetry.
Exactly.
That's cool.
Yeah, it's a really neat way to visualize these abstract concepts.
And it's not just about the abstract symmetry elements, right?
No, it's also about the actual shape of the crystal.
Or morphology.
Yeah, the morphology. So each face of a crystal
Yeah.
has a normal.
A normal.
Yeah, basically an imaginary line
Okay.
that points directly outward from the face.
Like perpendicular to the face.
Exactly.
Yeah.
And you can project those normals onto the sphere and then onto the 2D plane using stereographic projection.
Okay.
And by looking at the pattern of those projected normals,
Right.
crystallographers can figure out the symmetry of the crystal.
So it's like a fingerprint of the crystal's shape.
Yeah, you can tell a lot about a crystal just by looking at its stereographic projection.
That's amazing.
And this is really helpful for classifying crystals.
Right, because there are so many different types of crystals.
Yeah, there are thousands of them.
And they all have different symmetries and shapes.
Exactly. And stereographic projection helps us organize them.
So how does that work?
Well, there are these things called crystallographic point groups, which are basically ways of categorizing all the possible symmetries that a crystal can have.
Okay.
And there are 32 of them.
32 different point groups.
Yeah, it sounds like a lot,
Yeah.
but it's actually not that bad.
Okay.
And each point group has a unique stereographic projection.
So it's like a visual identifier.
Exactly. So if you know the stereographic projection of a crystal, you can immediately tell which point group it belongs to.
And that tells you a lot about its symmetry.
Yeah, it tells you everything about its macroscopic symmetry.
Your macroscopic symmetry.
Yeah, that's the symmetry that you can see with your naked eye.
Okay.
So for example, a crystal that belongs to the M3M point group.
M3M?
Yeah, it's a cubic point group.
Okay.
It has a very specific stereographic projection.
Right. That identifies it as belonging to that point group.
Exactly. And that tells you that the crystal has all these different symmetries.
Like what kind of symmetries?
Well, it has four-fold rotational axes.
So you can rotate it by 90 degrees and it looks the same.
Exactly. And it has three-fold rotational axes.
So you can rotate it by 120 degrees.
Yeah. And it has mirror planes.
Mirror plane.
Yeah. So you can reflect it across those planes. And it still looks the same.
So it's a very symmetrical crystal.
Yeah. It's one of the most symmetrical point groups.
Cool. So stereographic projection helps us classify crystals based on their symmetry.
Exactly. And it's not just for single crystals.
Right.
You can also use it to study polycrystalline materials.
Polycrystalline materials.
Yeah. Those are materials that are made up of lots of little crystals all stuck together.
Okay.
And each of those little crystals has its own orientation.
Right. So they're not all lined up in the same way.
Exactly. And that can affect the properties of the material.
Like its strength or its conductivity.
Yeah, exactly.
So how does stereographic projection help with that?
Well, you can use it to create something called a pole figure.
A pole figure?
Yeah, it's basically a map of the orientations of all the little crystals in the material.
Oh, wow.
So you take each little crystal and you figure out its orientation.
Right.
And then you project that orientation onto the stereographic projection.
Okay.
And you do that for all the little crystals. And you end up with this pattern of points on the stereographic projection.
Representing the orientations of all the crystals.
Exactly. And that pattern tells you a lot about the texture of the material.
The texture.
Yeah. So if all the crystals are oriented in the same way, then the pole figure will have a very sharp peak.
Okay.
But if the crystals are randomly oriented, then the pole figure will be more spread out.
So it's like a measure of how ordered the material is.
Exactly. And that can affect its properties.
So it's a really useful tool for material scientists.
Yeah, they use pole figures all the time.
And there are standard conventions for how these projections are done, right?
Oh, yeah, absolutely.
For different types of crystals.
Yeah, so for example, if you're studying a cubic crystal, you'll usually project it down one of its four-fold axes.
Okay.
But if you're studying a hexagonal crystal, you'll project it down its six-fold axis.
So there's a specific way to do it for each crystal system.
Yeah, there are these standard orientations that everyone uses.
And why is that?
Well, it just makes things easier. Everyone's on the same page.
Right, so you can compare results from different labs.
Exactly. It's all about consistency.
And you mentioned this tool called the WolfNet.
Oh, yeah. The WolfNet is super useful.
What is it?
It's basically a grid
Okay.
that you overlay on top of your stereographic projection.
And what does it do?
It lets you measure angles.
Oh.
So you can measure the angle between two crystal faces or the angle between two crystallographic directions.
And why is that important?
Well, those angles tell you a lot about the crystal structure.
Right.
So, for example, if you know the angles between the faces of a crystal, you can figure out the symmetry of the crystal.
So the WolfNet is like a specialized protractor.
Yeah, you can think of it like that.
That's awesome.
That's a really handy tool.
It's amazing how Henry Segerman's artwork, with this seemingly simple setup of a sphere and a lighthouse, offers such a direct and insightful way to understand this concept of stereographic projection.
Yeah, he really has a talent for making these complex ideas accessible.
And it's not just an abstract mathematical trick.
No, not at all.
It has this profound and incredibly wide-ranging importance.
Yes, it's everywhere.
Connecting artistic expression with scientific research.
From crystallography to cartography to theoretical physics.
It really makes you think about how these seemingly abstract mathematical ideas can have these unexpected and elegant manifestations in the physical world.
Yeah, it's all connected.
But across so many different disciplines.
Math is the language of the universe.
It really invites further exploration.
Yeah, definitely.
Into these fascinating connections between math, art, and science.
There's always more to discover.
Absolutely. All right, well, that's our deep dive for today.
Thanks for having me.
It was great having you.
Yeah, it was fun.
See you next time.
See ya.